So by now we're starting to feel relatively comfortable with infinite series, and we've seen a few where we can explicitly calculate what the series converges to. In general, this is not an easy thing to do. However, we're also able to usually estimate how close we are to a limit of a series if it exists. But that means that we need to know when a series converges. So this is a very important question. When does a series converge? That is a great question. Unfortunately, there's no hard and fast rule that says yes, this will converge and this won't. What you do have are some tools for deciding when a series converges or not. The first most important tool basically will tell you if a series diverges. And it's a little weaker, of course, than convergence, but at least it tells you where not to go looking. And so this is called the divergence test. And the divergence test basically says that if the sum k equals 1 to infinity, ak, converges, then the limit as k approaches infinity of ak has to be 0. In particular, if limit as k approaches infinity of ak is not equal to 0, then we definitely know that sum k equals 1 to infinity ak diverges. And this is really how you use the divergence test. You use it in the following manner. You basically check this limit of the sequence of terms, and if that's not 0, then you know that you're cooked. So for example, if ak is just the sequence of ones, clearly sum k equals 1 to infinity ak diverges. The idea is that if I am converging to a constant, then eventually the numbers in a tail of the sequence are starting to look constant. In particular, that means that I'm just summing constant after constant after constant, and so that looks like n or so times some fixed number, and that will always diverge. Here is a crucial note. If you didn't catch it from my emphasis before, this cannot be used to show convergence of a series. And it's very tempting to do this. When you first see this as a tool, you say, oh, well, the limit of the entries is 0, and therefore I have convergence. But it is not the case that this works out. And the classic example is that of the harmonic sequence. So the harmonic series is the sum sum k equals 1 to infinity 1 over k. With partial sums Sn equals sum k equals 1 to n 1 over k. So it's a fact, and we're going to try and justify this. This series diverges. Even though the limit as k approaches infinity of 1 by k is equal to 0. Right, so just because these terms are going to 0 doesn't mean my sum is going to work out in the long run. That's the important caveat. So now let's go ahead and try and justify why these partial sums will fail. Well, let's look at the sequence as a graph. Let's say we have 1 here, 2 here, 3 here, 4 here, 5 here. Well, 1 over 1 is that. So this is 1 over 1. 1 over 2 will be 1/2, which will be right here. 1 over 3 will be about here. 1 over 4 will be even smaller. And then 1 over 5, even smaller than that. So these are the terms in the sequence that defines the harmonic series. So this is the harmonic sequence. So now one way to view this sum is, well, I have 1, and now I'm going to basically fill out this rectangle. I have 1 here, and I have this rectangle. And then I have 2 here, or 1/2, and I fill out this rectangle. Then I have 1/3 here, I fill out this rectangle. And then I have 1/4, I fill out this rectangle. And I have a 1/5, I fill out this rectangle. And then I view this series, the series, as the sum of the areas of these rectangles. Now this starts to be reminiscent of an integral. And what's it the integral of? Well, the function is 1 over x. So what will 1 over x look like? Well, 1 over x is going to do this thing. 1 over x will meet those, but it goes further down than this rectangle. So it's always less than or equal to this step function defined by my rectangles. In particular, this is the integral from 1 to 5 of 1 by x dx. And what's that equal to? Well, it's equal to the log natural of 5 minus log natural of 1, which is just log natural of 5. And so I have an expression for this area, and in particular, this area, whatever it is less than, I can see that it's strictly less than the partial sum at 5. So the partial sum at 5 is the sum over these areas. So that's pretty nice. But here's where we get into trouble. Here's where we get into trouble. And in fact, we can establish immediately that via this geometric reasoning, that the log natural, we can establish immediately using this geometric reasoning that, in fact, log natural of n is always going to be less than Sn. But here's what happens. What's the limit of log natural n as n approaches infinity? This thing goes to infinity as n approaches infinity, and it's a lower bound on each of the Sn's. So that means that the Sn's have to be growing in an unbounded fashion. So we know that this will have to approach plus infinity as n approaches infinity. Now this was really cool geometric reasoning. So we could relate our infinite series to just a simple integral. Now you might be tempted to say that, well, these integrals coincide, but in fact they will not. And in fact the difference, there's this difference area that you can calculate, and that difference area is known as the Euler-Mascheroni constant. So we've just shown that the harmonic series diverges via this integral reasoning, and in particular this reasoning gives rise to what's known as the integral test. And here's one thing to note about the integral test. Unlike the divergence test, sometimes called the test for divergence, the integral test can sometimes be used to establish convergence of a series. So what is the integral test? Well, the integral test, we're basically going to relate our infinite sum to some integral. So this is a theorem in the book. So suppose f is a continuous positive decreasing function So for example, our 1 over x worked for x greater than or equal to 1. And suppose further AK is actually in agreement with this function at the integers. Then the sum k equals 1 to infinity AK and the integral from 1 to infinity, this improper integral, f of x dx, either both converge or both diverge. Note, if they both converge, it is the case that the two limits or two values are not equal. So even if they converge, so before we knew they definitely couldn't be equal. One is going to be a strictly larger area, and we know that that difference ultimately is going to be an Euler-Mascheroni constant. However, if they both converge, even in that case, these two values are not equal, and that's something to be careful of. And here's the rough picture of what's going to happen here. You have this decreasing function f. You have a decreasing function f. And basically, at the integer values, you're going to have agreement with the sequence. Well, you have agreement with the sequence, and so we know that definitely we can again do this rectangular lower approximation that tells us that, well, this integral ultimately will be a lower bound for the sequence. So that tells us it's a lower bound, so that obviously if the integral diverges, then this thing will also have to diverge. However, we also get this thing as an upper bound of a tail of the sequence, because we can always see that by instead taking the right endpoint as an approximation, this will be the sum, this will be the area under here will be A2, the area under here will be A3, the area under here will be A4, and so this integral is actually a upper bound on the partial, or on the sum where we've left out A1, so where I just add A2, A3, A4, A5. Whereas these areas are A1, A2, A4, A3, and so on.